Hey everyone, today I'd like to solve this problem for you guys, but I'm going to change my strategy a little bit here. I'm going to go ahead and solve this problem as if I received it on my FE exam. I'm going to go through the solution as fast as possible, just kind of talking through my thought process concisely. Then later we'll refine the solution. We'll go into the official FE Reference Handbook and make sure we find the relevant equations and just explain the thought process and how we locate those equations if you don't remember them. So let's get right into it. It says a rod is constrained and loaded as shown in the diagram above. The reaction at the right wall is most nearly. Okay, so now that we're at a blank sheet of paper, first thing I would do is we're looking for reactions. I'll draw a free body diagram. Because that 60 kilonewton force is pushing towards the left, I draw both my reactions towards the right. I wouldn't waste my time writing an equilibrium equation because you can see there's only one equilibrium equation. The sum of the forces in the x direction equal to 0. We'd have two unknowns there, so that's not going to help us. This problem is an indeterminate problem, and what that means is that there's more unknowns than there are equations. We have to bring in an extra concept, which is deformation. And deformation for the case of uniaxial loading is given by the equation PL over EA. How could we use this equation to get that extra deformation relation that we need to solve the problem? Is that we know these ends here. These ends are fixed, so that means their deflection is equal to 0. That means that if we sum the deflection between these two sections, section 1 and section 2, what we should get is 0. And it's split up between two sections there because the loading is going to change. From one to the other, there'll be a change of 60. So what we know is that P1 L1 over EA plus P2 L2 over EA, that has to be equal to 0. They're the same material, same area, so that denominator is going to be gone. Let's take the ratio of L2 to L1, noting that the ratio of L2 to L1 is equal to 3. What we have is P1 plus 3P2 must be equal to 0. Now all we have to do now is find the internal axial load inside of section 1 and 2. Let's find it in terms of just the one unknown that we need, which is Bx on the right hand side. So inside of section 1, the internal axial load is a tensile Bx, and inside of section 2, the internal axial load is a tensile Bx minus a compressive 60 kilonewton. Let's go ahead and plug that into this relation here on the bottom. P1 was Bx, and 3 times P2 is Bx minus 60. That entire value must be equal to 0. We have 4Bx equal to 180, and that Bx is equal to 45, and all our units were in kilonewtons. And let's go ahead and check the answer now. 45 kilonewtons. Okay. Seems correct here. You can see the explanation here on the bottom. So let's go ahead and read through this. Firstly, we had to recognize that this problem is an indeterminate problem. It's indeterminate because there are more equations than there are unknowns. So you can see that no equilibrium equation was written here. Now, one thing that could be confusing is that these internal axial loads, Bx and Bx minus 60. Let's go back to the blank sheet of paper and make sure we clear up that. What we're doing to find these internal axial loads is we're drawing a free body diagram like this, making a cut, and you can see that this small rod section over here would have a Bx and a Bx here. This one is the reaction force, and this one is the internal force. That's the force P1. And you can see it's tensile, which is why I made it positive. And then we can also draw a second free body diagram here of this outer section. If we free it, what we have is an unknown internal reaction. That's the P2. We have a Bx here, and we have the 60 kilonewtons. If we sum the forces in the x direction here, what we get is that Bx minus P2 minus 60 equal to 0. P2 is equal to Bx minus 60. Now, how I did that so quickly, let me explain it to you guys. If the action of a force is tensile, its reaction will also be tensile, which is why I said this is a positive Bx. Again, if we look over here at the Bx minus 60, we have a tensile reaction. So that means the internal will be tensile. We have a compressive external force. So that means it's going to be a compressive reaction. It's compressive because it's pointing into the section. If you're enjoying the video thus far, please like and subscribe to see more content like this. Thank you. Another thing is that if you didn't remember this formula, deflection due to a uniaxial load, it might take you some extra time to solve a problem like this. First thing I would do is, if we look in the handbook, because this problem is about deflections, we know that it's not a statics problem, must be a mechanics and material problem. So let's go ahead to that section. We know that we're dealing with uniaxial loads. We have an axial load in a cross section. The deflection is equal to PL over EA. So that's how we would locate that formula. It's on page 131 of the reference. You can see I kind of noted it down here. Okay, so now that we have information where we know how to find the formula and we explain that internal load, I think all of the issues with the problem are cleared up. If you enjoy seeing me solve these FE exam problems, I'll be bringing out more content like this, so please like and subscribe. You can leave a comment below and let me know what kind of questions you want to see me solve next. You can also check out my app, FE Interactive, in the description below. Use referral code Engineering Fundamentals for a month free when you subscribe. Thanks for watching. Goodbye.